if you did have an energy level where this is lower than this, then that would be a violation of the Heisenberg uncertainty principle, because the Heisenberg uncertainty principle gives us this, right? Gives us this, because this, where is it? Here again, is more or less the same as this, but this value here is what we deduce from the Heisenberg uncertainty principle. So you can't get less than this, because if you did, that would violate the uncertainty principle. You would have a delta x delta p smaller than what the Heisenberg uncertainty principle allows. All right, so it's not allowed. So you therefore, after all that reasoning, therefore you cannot have an energy level corresponding to an x where your x lies between 0 and pi and 2. Right? The Heisenberg uncertainty principle forbids it. Okay, all right. So, oh yeah, the philosophical thing. So you remember me, quite a few sessions back, posing the question, was more a philosophical type question, existential, epistemological question in interpretation of quantum mechanics. Is the uncertainty of our knowledge about momentum and position, is that just due to the clumsiness of our measuring instruments, because we're using photons to measure the position and the momentum, but photons themselves are quantum particles, so to have a certain accuracy you need a small wavelength, but a small wavelength corresponds to a high frequency, and hence the photon has a higher energy, more momentum, more kick, and it disturbs what it's trying to measure more greatly. So if you had, hypothetically, if pigs had wings, if you had sub-quantum particles that didn't disturb that way, would that mean that the Heisenberg uncertainty principle would go out the door? I mean, is the Heisenberg uncertainty principle due to the clumsiness, the brutishness of our measurement techniques, or is it somehow intrinsic to nature itself, irrespective of the clumsiness of measurement? Right? Well, when you look at think about these kinds of things, it seems to suggest that the Heisenberg uncertainty principle is somehow intrinsic to nature, right? Because you keep coming across this kind of reasoning, and there's no question of measurement here. We're not disturbing anything. We're not looking at anything. It just seems to come out. This seems to fit the data here. So we're not measuring anything, but we can use the Heisenberg uncertainty principle to deduce that no energy level can be found in that range, where x ranges between 0 and pi and 2. And this kind of reasoning keeps cropping up. So a lot of physicists feel that the Heisenberg uncertainty principle is somehow intrinsic to nature. Right? It's not just a simple issue of the clumsiness of your measuring devices, using photons, which are themselves quantum systems, which inevitably give your system a kick. Right? So food for thought. Right? So now you're probably sensing already that as we get deeper and deeper into quantum mechanics, it seems to become more and more about the formalism, how the mechanics, in a different meaning of the word, the sheer mechanics of solving Schrodinger's equation, and essentially the math, but less and less about the interpretation. What does it all mean? That seems to go by the board somewhat, unless you specifically bring it back in. And later I'll do whole courses on the interpretation of quantum mechanics, because it's so interesting. Right, well, okay, so a little bit of philosophy there. Now, let's actually look at some actual results for a given gamma. Remember, you can have any size gamma you want, effectively, as long as it's positive. Right? So let's choose a particular value of gamma. Let's say this one here, so you choose a gamma such that V naught A squared is pi squared h bar squared over m. Now the smallest was when you had it 8m, right? Any smaller than that, and you violate Heisenberg uncertainty principle. But anyway, this is 8 times larger than this lower limit, right? So choose a particular. It doesn't really matter which one, but so we'll choose a gamma such that this is true, and so we know the gamma, and so we can do this kind of thing and get solutions. So let's find the first three for this value of gamma. Let's find the first three solutions, the first three eigenfunctions, the first three wave functions, right? So so when you do that, they turn out to look as follows. So you got sort of like a bell curve type solution to your first allowable energy, and it has even parity, right? And here's your first odd parity. It sort of looks like a, I don't know how to describe that, like a roller coaster ride, but of odd parity, right? And then the next one up, the third allowable energy, for this gamma. Again, you get an even. Parity is even, so you get a symmetric function. It looks like this. Okay. Now, interestingly, your wave function is non-zero, fairly close. Well, you're just outside the barrier, the A and minus A. You can see here that your U here is non-zero, but it decays away very rapidly. In fact, exponentially. That comes out of mathematics. So, but still, at A, it is non-zero. Okay, but it does decay away exponentially to zero. So you can call these two regions here, just a little beyond the barrier of A and minus A. Call them the wings, right? Because they're sort of on the edge. They're the wings. Here. Now, what these three all have in common is the values of the wave functions in the wings decay to. That's the right word. They reduce. They go down exponentially. Okay, that's true of all these cases. So which is what I've just said here. So U decreases exponentially with the distance as your x moves beyond A or down beyond minus A. Right? Now, as the depth of your well, your potential well, as it goes to infinity, so it goes infinitely deep, then these wings here, the value of your psi function, your wave function, your eigenfunction, many terms, your U, right, many terms. Your U here, as your V naught goes larger and larger, your U here just disappears, right? The exponential drop-off is so severe that your U in this region, outside A and minus A, just drops away to zero. So as V naught goes to infinity, therefore beta goes to infinity, so your U goes to nothing in the wings, right? Now, but for a finite V, very close to this limit, you will have a non-zero U. Your wave function will be non-zero. Therefore, there is some probability, it might be small, but there is some probability that you will find the particle, beyond A or beyond minus A, right? From the probability density idea of Born, Max Born. Okay. All right. Now, all this so far, which I mentioned in the previous session, we were taking the case where E, the energy, was less than V naught. Okay. Well, now to tidy things up, pull in the loose ends, sense of completion. How about the case when E is greater than the depth of your well? So intuitively, what do you think would be going on then? Well, that means the energy is greater than the depth of the potential well. So intuitively you would think that the wave vehicle then would have enough energy just to escape the particle, the depth of the well. Right? It has enough energy to bounce out, to get out. Right? That's what intuition says. Well, let's try and prove it that that's what happens. Okay. Now, so if E is greater than V naught, then beta. Have a look at the definition of beta. I think it involves a, let's see, which would it be? A V naught minus E. So the definition of beta. Definition of beta. Yeah, it involves square root, various factors, V naught minus E. V naught minus E. Okay? V naught minus E. So if E is larger, then V naught minus E is negative. Alright? And we're talking square root. So beta now becomes a complex number. So I've written this here. Now, some of you, I guess, are following this quantum mechanics course, but did not follow my previous finite group theory, which is math. Anyway, this symbol here just represents the infinite set of complex numbers. Right? So it's just a big C, capital C. So beta belongs to the set of complex numbers, which is just a fancy way of saying that beta is a complex number. Right? So let's write it in this form. So beta, just let it say be I k. Now k is just a real. Right? So I just square root of minus 1. That's the form that beta will take. Right? So now in the region outside the barrier, when mod x is greater than A, in that region the general solution you had was of this form. Remember? U equals C E exponential to the minus beta x blah blah blah. Okay? Now beta now is ik, so plug that in for the beta here, and you'll get some new constant, just called C dashed, sine kx plus d dash cos kx. If you're wondering where that comes from, well, just plug in ik here and do the math. Right? Do that as homework if you like. Right? Anyway, so U takes this form. Right? Now, without going into the details, knows the text if you want. I haven't checked yet, but very probably the homework section, the exercise section at the end of the chapter, will very probably have something like this. But anyway, so then the usual thing, now use continuity normalization that will allow you to find values for A, B, and C dashed and D dashed. Right? You can actually, by using these conditions, you can find the values of those A, B, C dash, D dash, right? And so once you know those, that puts limits on the value of your alpha and your K. Oh, sorry, no limits. But this, rewind me. Okay, but there are no limits on alpha and K, and that implies that there are no limits on the energy. Okay. And that means that E can be continuous, and hence U, the wave function, it can be anywhere. Right? There's no restrictions on its position. It can just be anywhere. So in other words, it's free. It can get out of the well and just go anywhere it likes. Right? So that's sort of what you would expect classically, right? Expect that from the correspondence principle. Right? Now, in the next session, I will do the fourth example of a STI, and this time I will be dropping a ball in a gravitational field. So the potential energy then of that ball will depend on, let's say, the height above the floor. So let's say this ball is a bouncing ball, and it bounces off the floor. So when it's of height h above the floor, it will have a potential energy that's a function of that height, right? And so our V now will become variable with the height. It will not be fixed. And well, perhaps I'll leave it to then anyway. So that will be our fourth example, and each time gets a bit more complicated, especially the mathematics. So example number 4 will be called just simply the bouncing ball.